Swayam Prabha. Digital India. Educated India.
Hello. So welcome to this course on astrochemistry, and this is lecture 6. Before proceeding further, I shall first start with a brief recap of where we left in lecture 5. So until lecture 5, we had looked into the Big Bang nucleosynthesis, of the lighter elements. That is, we're talking about hydrogen and its various isotopes. Although, for lithium, I did not give you the equations, but for hydrogen and helium, we discussed how the various isotopes could be formed, starting from T equals 0 itself, and including the isotopes. So we have looked into this, and followed by that, we discussed what an interstellar cloud was. What was an interstellar cloud, and how the interstellar cloud gave rise to the idea of the formation of a star itself. The interstellar cloud collapses under the influence of gravity competing with the kinetic energy of the various atoms and molecules, and a star is born. But as far as astrochemistry is concerned, more than the formation of the star itself, we are interested in the debris or the disk that accrues around the star, and that eventually transforms into various celestial bodies such as planets, asteroids, and also comets. How they formed by the collapse of the interstellar or an interstellar cloud. And we also briefly looked into the differences between planets, asteroids, and comets, and the different types of chemistry that they bring into the table. All right, are we clear? So this is where we stand. Oh yeah, and before that, I also briefly introduced you, lastly, to the idea of what the interstellar medium was. Basically, the interstellar medium is nothing but, can you say what it is? It is nothing but the vast empty space, almost empty space between any two stars, excluding the disk space. So this is where we are in our course in astrochemistry, and I also emphasize that the discussion so far has only been qualitative. For example, I never told you in a quantitative way, that is, including a lot of equations as to what are the explicit forces responsible and how much energy is transferred, etc., etc. Those details we might look into in subsequent parts of this course. But for now, a qualitative description related to how the lighter elements were formed and how we have the generation of an interstellar cloud comprising of small atoms and molecules, and from the interstellar cloud, how the planets, asteroids, and comets are formed and what are the constituents of them. And finally, we now have come to a stage where we can define a new term called as the interstellar medium. All right, yeah, this is where we are at. Now, continuing further, so this is page 2. So, continuing further, let us now look into various aspects of the interstellar medium. Okay, so the interstellar medium has like two major components. the interstellar medium has two major components, one of which is gaseous in nature. We call that the interstellar gas. And that roughly occupies approximately 98% of the ISM. And can you guess what gas? Predominantly? Of course, it is going to be, most of it is going to be hydrogen, H, helium, of course, in various neutral and ionized forms. So this is the 98% gaseous form. What is the rest 2%? And approximately 2% of it is going to be in the form of what is called as dust. Now, what is your understanding of a dust? When I use the phrase dust, what comes to your mind? Tiny specks of particles, right? For example, it's a pleasant morning. You open your window and there is sun outside, and you see specks of dust, falling atop you, right? You can see them. So likewise, the interstellar dust, the interstellar dust comprises of very small solid particles. What these particles are, we'll see soon. Okay, so this solid state, that is interstellar dust, is approximately 2% by mass. Okay, are we clear? So 98% of the interstellar medium is like a gag in the gaseous state, and 2% is going to be in the solid state, and we call it interstellar dust. So the constituents of this dust is actually very interesting. Now in the gaseous state, we saw that predominantly we're going to have like hydrogen, both atomic and neutral hydrogen, atomic and molecular hydrogen, along with some helium molecules also, helium atoms, and in various ionized states. That is, it can be He plus, H plus, or H2 plus, etc., etc. All right. But what about the dust? What do you think? Let me ask you a question now. The question is, what are the constituents of interstellar dust? And you can as an ancillary question, can it be H, H2, etc., etc.? What do you think is the answer? Can it actually be H and H2? The answer is, well, of course, I'm asking a fact-based question. So unless you have access to the facts based on the experiments, you'll not know the exact answer. But what does your intuition tell you guys? Based on intuition, you would expect that, well, H, H2, these are all going to be weakly bound. Now, when they are weakly bound, the distance between any two atoms or molecules in a sample is going to be much larger, right? There are not any predominant forces of interaction between any hydrogen atom and another hydrogen atom, or like H2 molecules, etc., etc. Correct? This being the case, it is unlikely to be H or H2 itself. Okay, but rather, what is it going to be? Well, we also know that as part of the interstellar clouds, there are some molecules which could also be formed, correct? We saw the formation of the lighter elements, and even though we did not discuss how the other elements, such as, for example, beryllium, boron, carbon, etc., etc., how they were formed in the interstellar medium, but they could also be formed eventually by some nucleosynthesis process, even though it need not be exactly Big Bang nucleosynthesis itself. All right. So then, due to this, right, we have some other small molecules, such as, for example, H2O, or for example, MEOH, and we have carbon monoxide, for example, or also, some silicates, right? These could also be formed in the ISM, Because eventually, by nucleosynthesis, from the lighter elements, the heavier elements can also be formed. And once you have the formation of the heavier elements can combine with the lighter elements, right? And when you have two elements combining, you have the formation of a molecule. And what are those molecules possible? That can be water, methanol, carbon monoxide, silicates, etc., etc. This is not an exclusive list, etc. Okay, please note this. So the interstellar dust it comprises of clusters of these molecules. It can be, for example, water clusters. It can be methanol clusters, for example, carbon monoxide clusters, NMP, or like it can also be the silicate clusters, or a combination of these. Etc. All right. So when I refer to interstellar dust, I'm talking about loosely bound, weakly bound molecules held together such that overall they appear to be in the solid form, as tiny specks of dust. All right. They're also the dust are also called as interstellar ices because the temperature in the ISM is very cold, and all these molecules, they're all bound together by weak interactions. So they're also somewhat synonymously called as interstellar ices. Now note a key point here, a key chemical point. You have like H2O. Now with just one H2O molecule alone, the formation of a dust is not possible because H2O, because as you all know from a rudimentary understanding of chemistry, for the formation of a solid, you need multiple particles to come together. The particles are much closely bound than they are in the liquid or the gaseous state, correct? So you have the formation of many molecules of water happening, and they all come together, agglomerate to some extent, and form this thing called as dust. So this is the interstellar dust. Now at this stage, it is very natural for many of you to ask me a question. Now, when I talk about the interstellar medium, I referred to the idea that it has some gases and some molecules agglomerating together to form something called as dust. Why not the liquid, right? Have you thought about it? I referred to something called as a gas and something as a solid dust. Dust is of course solid, correct? Why not a liquid? For example, what are the common states of matter we encounter here on Earth? We encounter solids, liquids, and gases, correct? But I never mentioned anything about the liquid phase at all. What could be the cause? Well, hold on to your guns. I will explain the reason, in the upcoming lectures. Okay, there is a very special reason why I intentionally did not mention anything about the liquid phase at all here. Okay, so on that note, we shall proceed further. All right, so we now know that the interstellar medium comprises of gas and dust. However, note a very important point. The ISM, despite comprising only of gases and dust, is not a homogeneous medium. The ISM is not homogeneous. Now, what do I mean by not homogeneous? For example, just because 98% of it is gas, not all regions in the ISM are identical or even similar. There are going to be tremendous differences. Likewise, even among the interstellar dust, right? Even among the various interstellar dusts, there are significant differences. Are we good, right? So the key point to understand here is that the ISM is highly inhomogeneous or non-homogeneous. The interstellar medium should not be thought of as one single entity, as this vast space between stars, which it's not a homogeneous medium at all. All right, so please note that it is not one single region, it has multiple regions. So it has Alright, it has multiple regions. Now, what these regions are and what implications they have for the different types of chemistry, we shall soon see next. Okay, so the key thing is that there are different regions of interstellar medium, and what characterizes these different regions? What characterizes different regions are, of course, the same physical conditions that we study in our thermodynamics classes. What are the physical parameters that can easily be varied in space? Pressure and temperature, correct? Yeah, pressure and temperature are the two parameters. So likewise, in the interstellar medium, we have multiple regions depending on the state of matter that is present over there, and also the temperature and the pressure also. Okay, so we shall now look into the various kinds of regions in the ISM. I need the whole board, so I'll use it here. Different regions of the ISM. Well, so what exact different regions are there is actually going to depend on what galaxy you're talking about, right? Because in different galaxies, there could be different types of regions. Now, I'm going to illustrate to you using the example of our own Milky Way galaxy. In our galaxy, that is the Milky Way galaxy, what are the different regions of the ISM? Okay, so the regions, I'll make a small table here. Component, and the next one is going to be the volume it occupies, percentage volume occupied, and the next column is going to be the temperature in that region, and the next column is going to be the state of hydrogen. Okay, so these are the 5 components. The first significant region is called as molecular cloud. Now, what is a molecular cloud? I recall in the beginning of this lecture, I was discussing something about the notion of interstellar clouds, right? Now, if these interstellar clouds, you have some atoms and molecules. If predominantly there are molecules, you call it an interstellar molecular cloud. Okay, but notice that in terms of the fraction of volume it occupies in the interstellar medium, it's actually less than 1%. So you can imagine how sparse the interstellar medium is. But despite the interstellar medium being sparse, the molecular cloud, right, is actually pretty dense. It only occupies less than 1%. So it is this dense region that is responsible for a lot of chemistry of the molecules happening in the universe. Okay, so please note this subtle point. But why is it so dense? Why does it need to be dense? We'll actually be looking at the tutorial sessions. Okay, yeah. So the temperature in these molecular clouds are roughly of the order of 10 Kelvin or lesser. Please note, so we're not just talking about a dense region, it's also a very cold region. Okay, so the temperature is less than 10 Kelvin, and in fact the temperature might also explain the density, right? Because the kinetic energy of the molecules is so low at a very low temperature, right? The molecules are intact, and they're also kind of protected from very high ionization, external ionization, etc., etc. Okay, and what do you think is going to be the state of hydrogen? Will hydrogen exist as H or H2 or H2 plus or H plus? What do you think? Well, because again the temperature is 10 Kelvin, it is a highly dense molecular cloud, right? You would expect hydrogen to be predominantly as H2. Are we good, right? In other words, the state of hydrogen is going to be molecular. Okay. Next region that we are concerned with is what is actually called as the cold neutral medium. Okay, now in this region, the fractional volume of this region, it turns out, is less than 5% of the entire ISM. And what temperature can this region be in? The temperature range is approximately of the order of 100 Kelvin. It can be, plus or minus 100 Kelvin or 50 Kelvin or something, but it's approximately of the order of 100 Kelvins. And what happens to hydrogen here? Well, the point is, the difference between this molecular cloud and the cold neutral medium is that this cold neutral medium is significantly more diffuse and less dense than the molecular cloud. As a result, what can happen is some ionizing radiations, not exactly ionizing radiations, but at least some radiation, some UV radiations or some cosmic ray can impact the cloud much more. As a result, what happens is that H2 molecule can dissociate. What is the bond energy of H2 molecule? Of the order of 400 kilojoules, right? Of the order of 400 kilojoules per mole. So, because it is diffuse enough, it is not protected from the external interstellar radiation. Consequently, hydrogen predominantly gets dissociated. But notice still, it is going to be existing as H, but it is in the neutral form. It is not ionized. That's an important distinction. So hydrogen is still going to be in the atomic form here and is not going to be ionized. All right. So this is the cold neutral medium. The next state is going to be what is called as warm neutral medium. Now we are going to be in for a huge surprise here. Now, not in the fraction volume. This is approximately, it occupies 20% or less than 20%, let's say. So it's a significant volume of the interstellar medium comprises of the warm neutral medium, right? And what do you guess is the temperature going to be? We started off with say 10 Kelvin or less, and we discussed hundreds of kelvins. So what is the next order of magnitude? You would be surprised to know that while this is of the order of hundreds of kelvins, this is of the order of thousands of Kelvin. In fact, closer to, like 6,000 Kelvin. Okay, right? So notice the jump, notice the drastic difference in the order of magnitude between the cold neutral medium and the warm neutral medium. So this was the first surprise because it is not a continuous change in the temperature. In one region, you have like 10 Kelvin, and suddenly in another region, the temperature changes to hundreds of kelvins, and in the next region, it is of the order of thousands of Kelvin. Okay, please note this point. Now it's about 6,000 Kelvin, but even though the temperature is so high, hydrogen is predominantly still in the neutral form. It is of course not in the molecular form, but it is not ionized. Please make note of this point. Okay, and also you may be wondering at this stage, I am giving these data as facts. Okay, I have not illustrated or done any derivation to you to determine why this is happening. We will be, looking at this with a little more depth, as to using some energetics calculations once we study the chapter on thermodynamics as to why is it that here it is neutral but here it is molecular. Okay, for now, just take it for granted. Okay, the next region in the ISM that we are interested in is called as the warm ionized medium. Okay, so this is called as the warm neutral medium. This is the warm ionized medium. Now, this also, this is less than 50%. In fact, this is the most dominant form in the ISM, and the temperature is roughly of the order of 10,000 Kelvin here. And here, right, it is here that we encounter hydrogen not just in the atomic form, but also in the ionized form. That's why, in fact, it is called as the warm ionized medium, whereas the previous one is called as the warm neutral medium. Okay. Now, so this was the warm ionized medium region. The next region is called as the H2 region. Don't worry about the name H2 itself. For now, just take it to be H2. Okay, I'll explain why and what does H2 means subsequently. Now in the H2 region, which is less than 1%, again, it's also a very dense region in comparison to the other part. Okay, the temperature can be as high as approximately 10 to the power 6 Kelvin, or even 10 to the power 7 Kelvin in some cases. Okay, right? And what about the state of hydrogen? It's going to be ionized, H plus. All right. So this region is going to be highly ionized too. Are we clear? Yeah. Now there is one last region, and that is called as the hot ionized medium. Now this hot ionized medium is approximately going to be 70%. See these numbers, right? They should all, the overall volume occupied should add up to 100. Okay, but I have not been quantitative here, so there is, note that there is some approximation here. These are not strict equalities. I have a less than sign here, a less than sign here, less than sign here, and an approximate sign here. Okay, so overall they will add up to 100, but we're not concerned with quantifying the exact volume here. Okay, so please make note of that. So this is approximately 70%, and this is the dominant region in the ISM. And the temperature here, can you guess what the temperature is going to be? Oh, in fact, I made a small mistake here. The temperature here is also going to be around only 20 to the power 4 Kelvin. So the temperature in the H2 region and the warm ionized medium is of the same magnitude. There's not much difference. Okay, right? Please note this. It is here that the temperature is actually of the order of 10 to the power 6 or 7 Kelvin. Okay, please note. So the H2 region and the warm ionized medium, the temperatures are more or less the same. In fact, this is a very important point. In a subsequent lecture, while we discuss the concept of what is called as number density, this becomes important. I will explain that to you, very soon. Okay, so please note this. In the H2 region, the temperature is also around 10 to the power 4 Kelvin and not 10 to the power 6 Kelvin. The 10 to the power 6 Kelvin range is for the hot ionized medium, and the state of H is of course going to be H plus. In fact, please note, so I will just call this page 8. I will continue from here. Okay, so please note that in the hot ionized medium, it is not just hydrogen that is ionized, but if at all there are other elements, right, even they are ionized. For example, in the hot ionized medium, I'm going to call this Him. All right, yeah. So in the hot ionized medium, not just hydrogen, but if other elements are there, they shall also be ionized. For example, we're talking about C plus, or we're talking about, yeah, even N plus. You would be so surprised, right? Well, N plus, nitrogen, one atom of nitrogen in the positive state. Weird, right? Welcome to the chemistry happening in the ISM. All right. So even these very unexpected species, highly unexpected species, such as C plus N plus, can also form in this hot ionized medium. Are we all good, right? If at all they are found, that is the key. Okay. So what did we see so far in this lecture? We saw that the interstellar medium is not a homogeneous medium. It has various different regions. Okay. And in the different regions, we have the opportunity to study different types of chemistry. Although the predominant one responsible for the formation of molecular evolution, that is the formation of larger molecules from smaller molecules in space, is the molecular cloud region. So this is the most important region, you can kind of say it. Not just that, the cold neutral medium also has to play some role. Okay, but beyond that, in the warm neutral medium, warm ionized medium, H2 region, hot ionized medium, etc., the chemistry is predominantly that of hydrogen, H plus, and perhaps He also. All right. So with that note, I will just summarize what we saw in today's lecture. We understood that the ISM comprises of interstellar gas and dust, and we saw that the ISM is a non-homogeneous medium. Okay, and it comprises of different regions. On that note, I will end today's lecture, and in the next lecture, we shall see the very interesting topic. We shall look into the very interesting topic of how the ISM is both similar and different with respect to our Earth. Okay? So with that, we end this lecture. Thank you. Have a good day.